Okay, welcome back. Today we're going to be doing the isentropic efficiency of a turbine. Okay. But basically the efficiency in general is defined as the actual performance divided by the isentropic performance. Okay, in this case, really isentropic performance means like ideal performance. All right. Okay, so more definitions for the isentropic efficiency or the efficiency will be, for example, what would be the efficiency could be a definition like what would be the actual performance considering that the system is irreversible. Okay, so basically in the actual cases you will always lose some type of energy that you cannot recover. So basically your change in entropy will be different than zero. And then this one will be, the isentropic will be the ideal case. That will mean that you don't waste any energy, so it will be for the reversible. Okay? I'm just trying to give you general definitions. Alright, now let us look at the case of a turbine. So a turbine, the general drawing for the turbine will be this. What is the function of the turbine? The function of the turbine is to create power. So let's say this is a shaft. So basically it will create power, and this will be our control volume or open system. All right. So basically, what is the function of the turbine? Is to generate power that will be for the irreversible, so will be for the actual case, and this will be for the ideal case, let's say the isentropic. All right. So in general, in these problems, you know, for the turbine is always some type of mass flow coming in or out. So in most cases, the definition is given in function of mass flow as well. So you have this divided by the mass flow. Okay. So what should be the actual work? If there is no loss of any form, should be, and this is, let's say, 1 and 2, the work should be equal to H1 minus H2, and this should be divided by H1, in the ideal case, would be H2S, where nothing is lost. Okay, so that's basically the expression. The actual work divided by the isentropic, then it will be just S for isentropic. Alright, so we need to do a figure for this. Generally, people will show this on an HS diagram. So this will be here, let's say your curve, and let's say you go here through two lines of different pressure, P1, let's say P2. So let's say first one, let me try to do something that makes sense. So this will be 1 here. So what happened in a turbine, you go from a line of high pressure and you will go to a line of lower pressure over here. So you have the high pressure here, this will be lower pressure. So the system is isentropic. What does that mean? That S1 should be equal to S2. So you go from this line directly to this point here, to this will be the isentropic. Okay, so the one we define over here. Isentropic. So will be the ideal case. But in real life, what really happens? We know that we're going to lose some energy. We're going to waste some energy. So that means that the S is not going to be equal to S2, so it should be, let's say, somewhere over here. So let's say this is 2S, this will be 2. So the actual, let's say, will be over here. All right. So we do just from the figure, the efficiency will be equal to what? The efficiency is just equal to the change in height between this point and this point will be what? This will be H1 minus H2, and you see that's why it's H1 minus H2 and not H2 minus H1, because H1 is larger, and this one here will be what? H1 minus H2S. So that's basically what you have graphically. Okay, so let's summarize. Like everything, depending on the component, in this case the turbine, the efficiency is always what will be the actual performance of the system divided by the isentropic. Okay, in this case, this is the equation. Or if you want to think about it, actual performance, you always have some losses, so the system will be irreversible. Isentropic means basically in the ideal case that you will be assuming that the system can act in a reversible way. So I'm going to finish this video here and let's do the first example.